So we are going to talk about Runge Kutta method. So Runge Kutta method is a higher order method to solve a ODE. And you see that, for Euler method, you have only one formula. And it's very simple, but the errors is very big. And then people try to come up with a more accurate method. So Runge Kutta method is one of the high order methods. And you can see that in order to get to high order methods, the formula is a bit more complicated. And so a general formula of Runge Kutta method of order nu, is given by this general formula. So you have xi1, xi2 up to xi nu. So nu is the number of stages. Okay? And then you define xi1 based on y0, xi2 based on xi1, and xi3 based on xi1 and xi2, and so on. So essentially, you can define xi1 up to xi nu explicitly. And so this is called an explicit Runge Kutta method. And once you have all the new temporary variables, you can define the next yn plus 1 based on this formula. And now we're just going to focus on Runge Kutta method order 4. So this is like the most popular method for solving ODE. And the Runge Kutta method order 4 is given by this table. So this table recorded the coefficient C, coefficient B, and the matrix A. So the matrix A is here. So the matrix A, so you have A11 is here, so there's 0, and then A21, A22, and so on. So this is the matrix A is denoted by capital A here. And the vector C, so the vector C, you have C1 here, C1, C2 here, and Ci. And the vector B, so the vector B is here, in this the last formula. So now it is recorded into this table, and now our task is we have to write down the formula for this table using this general formula. So we do it step by step. So this one, it has 4 rows, so the number of stages is equal 4. So nu will equal 4. And then we have 4 rows, so we have 4 temporary variables, so xi1, xi2, xi3, and then xi4, because it stops at xi nu. And then we use the general formula, so xi1 is just equal y0, and xi2 will equal, so this one should be yn, not y0. So xi1 should be yn, and then xi2 will be yn plus, so h, okay, and now a21, so this one is a11, so this one is a21. A21 is the second row, first column, and A21 is 1/2, so you have h over 2, okay, and then you have f of Tn plus, so C1 equals 0. So there is nothing here, so just 0, comma, xi1. And then xi3, so xi3 will be yn plus, okay, so now you have to take A31, so this one is your A31, but because A31 equals 0, so you don't write anything. So this one is A31, and this one is A32. So A32, so because it's 0 here, so I have to start with A32. So A32 is here. So A32 is 1/2. So you have h over 2, then f Tn plus C2h. So C2 is 1 here, so C2 is 1/2. So h over 2 and xi2. Okay, so this one is C1 and this one is C2. And then you have you have A32, and because there's no entries here, so it's 0, so you don't have extra term here. So then the last one will be xi4. So xi4 you have yn plus, so this one is A41. So A41 equals 0. So A42 equals 0. But now this one is A43. Yeah, so we have to put A43. So A43 is 1 multiplied by h. Yeah, so what is the last formula? And then f of the n plus, so this one will be plus C3, yeah, and plus C3, so C3 is here. So this one plus C3, so C3 is 1/2, so h over 2 and xi3, yeah. And that is for temporary variables, yeah, according to the Runge Kutta method of order 4. And then the last formula will be yn plus 1. So yn plus 1 will be yn, okay? And now you have to sum over on the bj. So you have to take h, yeah? So h with the common term. And so b1, so b1 will be 1 over 6 f of the n plus c1, so c1 equals 0, so there's nothing here, so xi1. And then the next one will be 2 over 6 f of the n plus c2 h over 2, so plus h over 2 xi2, and then plus, so this one is b1, yeah, and b2, b3, and b4. So this one is b1, 1 over 6, b2 is 2 over 6, b3 is 2 over 6, f of the n plus c3, so c3h, psi3, and the last one is h over 6, so sorry, 1 over 6 f the n. So now c4, so we have to take c4, so c4 equals 1, so plus h xi4, and the whole thing multiplied by h. Okay, so this is the formula for Runge Kutta method of order 4, and all the coefficients are given explicitly in this table. And you see, from this formula, then you can write a MATLAB program to implement the Runge Kutta method of order 4. And you know, I mean, if you've tried to implement it, you will see that the errors for Runge Kutta method of order 4 is much smaller than the Euler methods.